the next thing to do is look at what happens when atoms share. And so I'm going to show you how this is done. And sort of this method just helps you see like how it works. It doesn't always work to draw Lewis structures because when atoms share, they kind of break some rules and they kind of just move electrons around as they need to. So we have two methods for drawing Lewis structures. Most of them can be drawn with what I'm just about to show you. And then there's another method which is a little bit more complicated, but it ends up usually with the same result and can always draw Lewis structures for molecules. Like I said, the simple method I'm about to show you doesn't always work, so you should probably learn both, okay? All right, so we're going to start with hydrogen. Hydrogen has one, and this is the super simple way, right? That's hydrogen. It's in group 1. It has 1 valence electrons. So now hydrogen, the element, is H2, right? So the way H2 works is like this. I have 2 hydrogen atoms, and again, I'll just draw one of these in a different color real quick, like that. And when they come together, what happens is they share a pair of electrons. Draw one of these in a different color again, like that. Now, remember we were talking about the octet rule. For hydrogen, it's a little different. It's small, right? And its closest noble gas is neon, and neon only has 2 electrons in its outer shell. And so this hydrogen, right, has the 2, and this hydrogen has the 2. So they sort of both get what they need by sharing the electrons and mimicking helium's noble gas configuration, okay? Now, the electrons really are like the glue. So you think about this is a negative charge. And then out in the nucleus, has a positive charge. So when they're sharing the electrons, what ends up happening is the 2 atoms end up sort of gluing on to those pair of electrons, and that's actually what keeps them together. It also keeps them from like breaking apart and sharing those electrons with someone else unless you provide energy to first break that bond apart. So you think about a candy bar, right? So if you have 2 kids in the same size and you hand them one candy bar, right, and they fight over it because you only bought one, and so they're going to grab onto it and they don't want to let go, right? Because they want their half of the candy bar. Now, good kids, of course, will cut the candy bar in half and share it evenly and all that kind of stuff. But if you sort of have that visual in the head of the candy bar, that's the electrons, right? If you only have enough for one person, then what they end up doing is sharing that candy bar between the 2 of them. That's what creates their bond. So we're going to do this again for fluorine. And so fluorine looks like this, right? And then it has 7 valence electrons. Again, going back to our periodic table. Again, you always have to do this, right? Fluorine's over here. It's in group, 17 over here. And so I'll draw 7 valence electrons for 1 fluorine like this. Again, it doesn't matter where the dots are, but if I'm drawing bonds, I usually draw the unpaired dot towards the other atom. It doesn't really matter. And here's the other one. I'm going to draw it like this, and I'm going to use the fuchsia is what this color is, dots, to represent this. Right now, you notice that fluorine has 7, but needs 1 to get to 8, and both of them are that way. So what they end up doing is they end up sharing the pair, right? And you end up getting a bond between the fluorine atoms. So it'll look like this. Now, if you count electrons on both of these, right, you go like this, that's 8, and you count on this one, that's 8. So they both have 8 electrons. And they both satisfy the octet rule that way. So that is fluorine when it bonds. And so this bond that is in between them, this is the bonded pair, right? And then these are called either lone pairs or non-bonded pairs. Okay, so Having said that, there's another way to draw this, and this is maybe what you're familiar with seeing from other science books or other books that you've looked at. You draw the fluorines, and you draw a line between them like this. This represents a single bond. Now, in most drawing styles for introductory chem, you still have to include all these dots around here, and I'll talk about that in a second. It gets kind of tedious to draw those. But a single bond is one pair of electrons. Now, there's instances where you'll have to share more than one pair, like 2 or 3, and those would be, instead of being called a single bond, would be called a double and a triple bond, and we'll go over examples of that in just a few minutes. Okay, so we're going to draw a simple Lewis structure, but these are the rules that generally that we follow. One, you need to decide which atom's going to be in the middle sometimes. Like if you only have 2 and it's like 2 oxygen atoms, there is no central atom. But if there's 5 atoms, right, one of them generally, for these structures that we draw, one of them will generally be in the middle. The ones, and the books have all kinds of rules on this, but this is the simplest rule that I can think of, right? Most unpaired, paired, I forgot my N too, most unpaired dots. So if you're looking at it, the Lewis dot is the one that has the most unpaired dots. That's usually in the middle, okay? We'll talk about that in a little bit in relationship to carbon, okay? The second thing that sometimes indicate that it's in the middle is that it's unique. It's like the one oddball. For example, SO2. All right. Sulfur is in the middle. It's the oddball. So oftentimes they give you all these other rules to follow, but these 2 rules usually get you there. Okay. Now, having said that, why did I set aside carbon? Because carbon is only got 4 valence electrons. So it goes like this. It has the most unpaired dots of any element, and so when we think about how carbon can bond, it can bond the most ways, right? Because it can make 4 bonds total. It can bond the most different ways than any other element because it has the most unpaired dots. So when you think about like human biology and how carbon is so central in like everything, it's like one of the main elements in our body. It's because it can bond in so many ways that it's ended up being like one of the central atoms that we find in life. Okay, so carbon can bond many different ways. So if you see a carbon in a structure, that's usually the central atom. If you see multiple carbons in a structure, so let's say it's like this, C3H, let's do H6 like that, right? Then what you would have to do in this structure is all the carbons would have to be stuck in the middle in a chain like this. So if you have multiple carbons, they're usually linked together in some sort of chain like that. So keep that in mind as you decide on like the skeleton or the sort of the structure of the structure, like how the atoms are going to lay out, okay? Then the next thing you have to do is you have to draw the Lewis dot formulas for all atoms. Now you may have already done that because you had to decide which one had to be in the middle, but if it didn't have one in the middle, you would have had to draw all the Lewis dots. And then you bond all the atoms to the central atom once, because there's no reason to draw it in a Lewis structure if it's not bonded to it, because we're looking at the structure of how atoms bond to make molecules. So if it's in the formula, it's connected to something. And so typically, right, you're going to do this step, bond all the atoms to the central atom to form a skeleton. And then if you don't have octets, right, then you look for double and triple bonds. And so we'll do examples of all of these things. And so let me just start with one real simple one. I'll do O2, and then we'll do another one. But O2 doesn't have a central, so we don't have to decide on the central atom because there's only 2 of them, right? So we're going to draw the Lewis dots like this. And I'm going to stop drawing them in different colors here. So instead of bonding it to the central atom to form the skeleton, actually we just bond them together when there's two of them. So we're going to go like this. Or you could leave it as dots if you like. Well, you know, I'll draw one more with color like this. So there's one from one atom, and the other dot comes from the other atom. Now, if you look at this structure the way we've drawn it, I put circles around, and we're checking for octets. So if octets are not satisfied, so part of this is we're looking for octets. So we're going to say 1, 2, 3, 4, 5, 6, 7. So I have 7 here and I have 7 here. So the octets aren't satisfied. In order to satisfy the octets, what you end up doing is sharing electrons from the atoms again. So we got to share a second pair, right? And then you'll end up with this. Now, where you draw the unbonded electrons doesn't matter, so it could be at the top or the bottom, but you know, or to the sides like I did here. So now look what happened. By sharing another pair, I ended up, if I circle like this, right, that's 8. And if I circle like this, that ends up being 8. So I satisfied my octets with a double bond, 2 pairs of shared electrons. So an alternate way to draw this would be to draw the double bond like this. And that would be, either one of those is acceptable as a Lewis structure for oxygen. The one on the left is like a Lewis structure. The one on the right is actually called a Lewis dot structure because all the dots are drawn. But that doesn't really, the distinction is not that important. Now, having said that, you're probably tired of drawing dots, so I'm going to write a little note down here. You can use lines instead of dots. So I'll warn you, this is something that I do in my classes, and I don't know if anybody else really does it, but you can draw it like this. I think there's a lot of instructors that do this. You don't see it in the books. It turns out when Lewis did his drawings, like in the early 1900s, he used lines as well, but his lines went out. So he had oxygen, and it would have looked like this. Because he knew that those pairs of electrons could be used to connect to other atoms, and so he kept them, I think that's why he did it, he kept them drawn as lines pointing, radiating out from the oxygen atoms. So, this is okay, as well as these other two methods, okay? So I already did oxygen, so I'll cross that off the list, and I'll do something else instead. We'll do fluorine, and actually we'll do nitrogen, and I'll do 2 other atoms, or 2 other molecules instead of that, okay? We'll stick with these guys here. Okay, so another structure we like to do is nitrogen, because it allows us to see how we would get a triple bond. So nitrogen gas is a diatomic element again, just like oxygen and fluorine, which I did earlier in the lecture, which is why in my head I was thinking I probably shouldn't do them over again. So I have nitrogen. If I draw the Lewis dot for each, it's going to look like this, because it's in group 5, right? So it means it has 5 valence electrons. And then I'll have 2 of them like this. Now I'm going to do this in sort of stages. Like when you do it on paper, you're probably going to skip all these stages. But you're going to want to bond them together once, right? That's that rule that I talked about up here. Bond all atoms to the central atom once to form a skeleton. If you don't have a central atom, you just bond them together, right? So you end up with that. And then you count, and you're going to go like this, right? You're going to have nitrogen and a pair and a nitrogen like this. And this. Oops, 1 on each. like that. And then you're going to go, oh, well, look, there's a draw a circle like that. And that one has 6, right? So it needs 7, 8. It needs 2 more. So this is the indication, like when this has got, they're both short, like this is 6 and this is 6. It's an indication that with more sharing, you get more electrons, right? So there's all kinds of analogies in life about sharing and all that, but I'll just pass on them. You go like this, right? You do another one and another one. So this is what we're going to do. This is nitrogen, and I like putting the lone pairs over here and here. Now, think about this. This is something that's really important. The total number of electrons never changes. You always start and end with the same amount. So nitrogen's got 5. There's 2 of them. There's a total of 10, right? So look at this. This is here, 2, 4, 6, 8, 10. That's all 10 electrons. In fact, the way I'm going to show you, the other way to draw this is basically just draw a skeleton and throw the electrons on and try to get the octets, okay? And I'll show you that here in a second. But you'll notice this is 8. But 3 pairs are shared, right? And this is also 8. So this means I can draw the Lewis structure like this, and this is a triple bond, like that, okay? So that's how you get to triple bond or double bond, is you have atoms that are bonded together, but both of them are electron deficient. That is, they don't have enough electrons to make 8, and so they end up sharing more electrons with each other to get there. Right, so let's do NH3. Nitrogen is going to be our central atom. And there's a rule here, right? And it's that hydrogen, and it turns out, and fluorine, but it's not in the structure, are terminal atoms. That means in a structure, they're always at the end because they can only make one bond. So they're on the outsides, and they're never part of the central skeleton of a molecule. So, for example, right, in this structure, that means nitrogen is like this, and the hydrogens will be surrounding it like this. It's the central atom because of that. Now, each hydrogen, we're going to draw the Lewis dot. So this is what I'm doing. I drew the skeleton. So this is kind of like, decide on a central atom, draw the Lewis dot. I didn't do that, but now we're going to draw the skeleton. So then we'll do the Lewis dots as well. So I'm going to draw a skeleton. It's going to look like this, right? And then hydrogen has 1 dot, and this hydrogen has 1 dot, and this hydrogen has 1 dot, and this nitrogen has 5, because it's in group 5, and you can, oops, I drew too many dots over here, 5, and so you can kind of see how this is going to go together. The nitrogen needs to make a bond 1 time to each atom like this. So you could draw it like that, or you could draw it like this, is maybe the way you drew it just now. Now, if I circle like here, all right, that's the 2 that hydrogen needs to be like helium, and they're all that way. But then if you circle the nitrogen, you'll notice that it has 8. So it has its octet. Hydrogen has its duet, is what they often call it, which I think is kind of silly. It has 2. And the result is everybody's happy. Everybody has their octet or their full valence shell. So the Lewis structure for ammonia will look like that. Okay. Now we're going to do nitrite. Okay. Nitrite is NO2 minus, so we're getting more complicated, right? So what do you think will be the central atom? Well, there's 2 things to go off of, nitrogen being just 1, so it's probably in the middle. And the other one is that nitrogen has 3 unpaired electrons in its Lewis dot. So if I were to draw the nitrogen out, it would look like this. If I'm drawing oxygens out, now I got to draw 2 of them, but they're going to look like this. And they have 2 unpaired, each one of them, but the nitrogen has 3. Since it has kind of like the most arms, it's going to hold all the others, okay? So what I'm going to do is I'm going to draw nitrogen in the middle with its structure like this. And I'll draw the oxygens on the outside. And it doesn't matter where you draw it. I'm going to draw it over here. So 1, 2, 3, 4, 5, 6. Remember, I like to make the pairs like face each other, right? So 1, 2, 3, 4, 5, and 6, like this. And so what's going to happen is the nitrogen is going to want to bond once with each one. So like in the process of doing this, you're going to draw something that looks like this. Okay, and if you're keeping up with the line thing will look like this. And then I have dots like that. Now you'll notice something here, like this nitrogen only has, if you count it, 7 electrons, and each of the oxygens only have 7 electrons. And so they each want to pick up an extra electron, which means more sharing, like a double bond, right? So what'll happen is this. I can either draw it like this. Oops, sorry. I want to put the O on the outside. I can either draw it like this, or I could draw it like this with all the other things filled in. So if I'm going to do the one on the left, right, then I'm bringing in a pair of electrons like this, and that's what gives me that structure. Or I could do it the other way, and that would give me the other structure. In terms of the lone pairs, they're going to be like this, right? That hasn't changed. It's just that where the dots are going is changing. It's going to look like that. Now, if I bring the extra electron in from the left-hand side, that actually means this oxygen still has a dot out here. And if I do it on the right-hand side and I make the double bond on the right-hand side, this guy still got a dot over here. So what do I do with that dot? Because there's no more sharing, right? So I left this off at the end because usually people don't see it right away, and it's easier just to not complicate things yet. But what does this mean? Right. When you're drawing these, by the way, you'll recognize, oh, I'm going to have to add an electron somewhere. Okay, but I wanted to point out you can draw the whole thing without drawing in the extra electron. It needs, this oxygen has 7, and it needs 1 electron to get to an octet. It's this add an electron that you have to do at this point. Okay, so having said that, all right, I would end up with my Lewis structures being this. And I'll draw this like this. Or it'll be the other way, right? It'll be like the flipped over version of it. And really, this is one of the, in terms of understanding chemistry, this is like one of the most important things to learn is how structures are put together. You may not ever have to redraw them, let's say in like a class on pesticide management or in a nutrition class, but it's important you understand what the structures mean. So you'll see lots of structures in those classes, and they will have similar properties depending on their structures. If you look at pesticides and classes of pesticides, they have a lot of things in common in their structures, and you can recognize the different kinds of pesticides based on their structures. The same way you can recognize different like nutritional things based on their structures, like carbohydrates and sugars and starches. All these things are related to each other structurally. Okay, so having said that, there's 2 of them, right? So which one is it? And it turns out the answer is both, okay? If there's more than one way to draw the structure, right, we draw them both, and these are known as resonance structures. Now these are ions, so we put brackets around it like this, and I didn't leave enough space here. I definitely didn't leave enough space to do all this stuff. But we would put this arrow that looks like a two-headed arrow like this in between there to show that these are two forms of the molecule, that the molecule is sort of in between. Like it's like the average of these two structures. It's okay at this level, I think, to think like it's going back and forth between these two, because the electrons are spread around, and in a sense it kind of is going back and forth, but they're spread around in the bonds like that. All right, so that is the simple way of drawing Lewis structures. It says highlight the lone pairs in each, but I think you understand, like, the lone pairs are like these guys here, right? These are all lone pairs. I think it would be too much to go ahead and go back through and do all the lone pairs. The bonded pairs are the ones that, are between the atoms, and the lone pairs are on the outside. Next thing is the more complicated way, and some of you may like this better because it's very systematic, and you just sort of can always get a good Lewis structure out of this. So we'll do that next.